what the language is written in. Error. The handy wavy part. Think JavaScript is compiled like C++ or interpreted like a basic script. The precise reality. JavaScript is written in C++, specifically the V8 engine, Chrome or Node.js is a massive C++ project. It is not translated to C. It is just in time compiled. So basically, you abstract it via EST and then compiled it just in time and then run it. So depending on the code that is being executed on your file. So when you like click that function, it will be compiled and run to that engine. That's why it's just in time compiled. The error of omission, you may think JS runs line by line. It doesn't. V8 reads your code, turns it into bytecode ignition, and then a second engine, turbofan, watches which functions you call a lot. If your call user.login 1000 times, turbofan grabs that code, turns it into machine code binary, and optimize it directly for your CPU, Intel or Apple M3. So since this is written in C++, this V8 engine are smart in that it actually remember the function that you call a lot, such as user.login, and then put that in a cache near to your CPU. But most of your code are just converted to bytecode, which is the netcode code, before you actually uh, pass it to a runtime or convert it to a machine code, which is this binary. Second is the prototype chain a tree. The misunderstanding, you called it a direct acyclic graph. The precise reality, while a chain is a simple dog, calling it a dog implies multiple parents. A JS prototype chain is strictly linear linked list. So the difference with JavaScript being a linked list and a dog of Redux is that linked list is just a type of a dog. So a dog basically is more kind of like could have a parent. So that's not JavaScript. A JavaScript is just a simple dog because dog could have like multiple parents. A JS prototype chain is a strictly linear linked list. So the prototype pattern of JS is a strictly linear linked list or a simple dog. An object can only have one prototype, or it can only have one like node or object linked to it. The impediment, if you think it's a tree or graph, you'll struggle with multiple inheritance. JS doesn't have it, so you can have multiple inheritance just like with Redux. If you want a doctor to have behaviors from user and staff, you can link to both. Because again, it's one-to-one connection like node to node. You cannot have parent to children relation. You have to use mixins or composition pattern to be able to implement that. And also Redux, like I think this is what Redux does under the hood, the mixins and composition that allows them to be able to use the actual dog. Third, Redux is a dog. The structural error, the hand wavy part, you said Redux is a dog because it's made of JS. The precise reality, Redux state tree is a tree, not a dog. So actually, Redux is not a dog. It's a tree. In Redux, every piece of data has one parent that lies above it. going up to the root store. So the slice is actually the parent of a data, and then the root store is the parent of that slice. Why this matters? If it were a dog, where one node has two parents, the immutability logic of Redux would break. So it's not, I think it's React that's dog. So basically, it also kind of like, it's tree, but it's a different kind of tree in which it only have one tree. It can only have one parent. So basically, it's kind of like with JavaScript node linked list as well, in which you can only connect one node to the other node. And then from data to the slice to the root store. Why this matters? If it were a dog where one node has two parents, the immutability logic would break. When you update a leaf node in Redux, you must clone every parent all the way to the root. If there were multiple paths, a dog, the shallow equality check, all state equal equal new state, would fail. So another thing is that when you want to update a state in Redux, the way they were able to avoid that is that you need to clone all the parents from the root to be able to copy its state and then just update it. Because if there were multiple paths towards like updating the leaf node, the shallow equality check, all state equal equal new state, would fail and would reverse the feature of Redux. Fourth, the hidden class. The most profound impediment, the error formation. This is what separates senior from staff developers. You know about prototypes, but do you know about shapes, hidden classes? In C++, the memory offset of a variable is fixed. In JS, objects are dynamic. To stay fast, V8 creates a hidden shape in C++. So the danger, if you create two objects in JavaScript, such as const A, in C++, the memory offset of a variable is fixed. So basically the offset, from the memory, the location reference is fixed. In JS, objects are dynamic because again, it could be scattered in a node in the memory. So to stay fast, V8 creates a hidden shape in C++, which is the hidden classes or shapes. The danger, if you create two objects like const A equal here x, key value x with the key x with the value 1, comma key y with the value 2, and then you create another constant b equal y, key y value 2 and key x value 1. You swap order. To you, they are the same. To V8, they have different shapes. V8 can optimize them together. This causes the optimization making your code 10x slower. So it might looks like it's just the same um, constant to you, just swapping their order in your code. But for V8 engine, they actually have um, hidden classes or hidden shapes. So they can optimize this so it will run slow because again the objects are dynamic. It uses node instead of using memory offset with like with C++. So advanced material with when you get into high performance React or Node.js, shape stability matters more than prototype logic or like sharing behavior with others. So FIP memory behavior is shared versus OS memory. The subtle error, you compare it to OS shared memory like a DLL or shared library. The precise reality, it's actually pointer aliasing. In the OS, shared memory is often about saving physical RAM. In JS prototypes, it's about property lookup. When you call u1.login function, the CPU isn't looking at a shared memory partition. It's literally jumping through a pointer to a different location in the heap. So in prototype, like just because it's a behavior it's shared doesn't mean it's pointing to the same memory location or shared memory with with OS. It's basically using just a property lookup in which like again we use node to like look up that related node next to it, such as jumping through a pointer to a different location in the heap with like the stock const or stock defined used to define it. Impediment, if you think it's a read-only OS memory, you might think you can change it, but you can. If you change user.prototype.login at runtime, every existing user instantly changes. So you can actually change that because those are linked. Think of this as node connected, user, prototype, and login. Since you were able to access those by jumping through a pointer to a different location in heap, and then every user pointing to it or that will point to it to the login will now have this different value that you update. OS shared library usually don't let a single process change the library for everyone else because so with OS like you're talking about the shared libraries really because again OS were library before but now it becomes like a combination of libraries. Now OS doesn't let a single process like change that shared library being used by the processes on your system because it has like do you call this it needs to tap into the administrator mode for it to be able to do that, and OS by design do not allow those kind of um, update. So summary of your areas of omission, the parser or compiler graph, you are missing the ignition or turbofan pipeline knowledge. Second, the heap versus stock. You likely don't know which variables live on the stock, primitives, fast, versus the heap, objects, low, garbage collection. So the variables usually like that lives on the stock is like we mentioned in the previous video is just the fast or the primitives that point to the actual object because objects usually are larger than the primitives. Third, the event loop versus call stock. You know syntax, but do you know how C++ handles libov thread pool to make single-threaded JS handle 10,000 socket connections? Your next step, to stop being handy wavy, you should look at how V8 represents an object in memory. So to answer your question, you need to connect the higher level code you see in your LiveKit repository like use video call.ts to the low level machines of the CPU, stock, and heap as described in operating system's 3 easy pieces. First, what does pop or destroyed actually mean? In OS step theory, the stock follows a last in, first out order. The pop, when your function validate token finishes, the CPU moves the stock pointer, ESP or RSP, back to the previous frame address. The destruction, the data isn't usually wiped, zeroed out immediately for performance reasons. Instead, that memory is simply marked as available. The next function call will just overwrite whatever was there. So in the stock, usually you don't actually remove variable when it is being the value are destroyed. It's just there, waiting to be overwritten. If that code has been transferred from program to a process, so that the next function call will just overwrite the value of that variable. The reference, you ask if it happens after the reference is returned. Yes, the function puts the return value like a pointer to a room object in the heap into a specific CPU register, usually RAX. So the return value are that you get from a heap, like a pointer to the room object value in the heap. Uh, so basically, the function that will like manipulate that variable, or kind of like do the pipeline, like combination of program or command line program that makes it looks complex, is actually what it actually doing is that it puts the return value like an object to that variable into a specific CPU register for the register to execute it, so that the register now will now transform that object in the heap into um, what it meant to be in the by that function, and then return the pointer to that variable, and then return as well to the heap a new value. Then the frame is popped. The calling function then reads the address from that register. So when we go back here, like a validate, for example, that's a validate token function. After that, return to the heap and to the stock. The CPU moves the stock pointer back to the previous frame address. Then in this end, the frame is popped. So basically, that's how it talked to the frame address. The calling function then So this the another function that will now um, use that variable will call that or will read that address from that new frame register or address. Second, the OS or CPU lifecycle: fetch, retrieve, and return. When your LiveKit app runs, here is the machine flow. First, code segment, the instructions. Your TypeScript is compiled to bytecode, V8, and the JIT compiled to machine code. So that's how you pass the bytecode to a runtime program, which is the engine, which then the engine will convert it to the machine code. This sits in the text or code segment. The CPU's instruction pointer points here to know what to do next. So the instruction pointer that we discuss in CPU architecture that decides how it would, the that put that code into the actual CPU, and then depending on if the code has like branch prediction, will like point again to the memory to get that any jump into a node from your app, and then put that back into the CPU with the function, and then transform it. The fetch. So after that, the CPU. So after the code segment, the instruction, the fetch, the CPU fetches an instruction from the code segment saying create a new LiveKit participant. So that's a function. Then third, heap allocations. The JS engines finds a free block in the heap. So what will find the free block is actually the JS engine that execute that bytecode, or the program that execute that bytecode, because again that's the memory currently running. Free block in the heap OS dynamic memory. It stores the participant's name, metadata, and stream status there. So since the engine has the code running in it, because it also has access into the OS memory, it will now find like an available memory. In it, it will store the participant's name, metadata, and stream status there. Think about it like from CPU now going out to load and store, right? And then going back to the CPU cache into memory. Fourth, the return to app. So the heap address, like for example, it now allocate that new memory, is handed back to the stack to say like, hey, this is the new like allocated memory transformed by this function that you can now point to be able to transform new function in your code. So your const participant equal dot 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 in use video code.ts is actually just a tiny 64-bit address sitting on the stock. Pointing to that massive object in the heap. So this stock is still it's also in the V8 engine, because it needs to be transformed into a process in order for it to point to the heap that is also in the memory. So the const participant equal that dot just points to that in use video code.ts code, just points to that newly allocated heap data, pointing to that massive object in the heap. So the key realization here is that the code is being compiled first, transformed from the program written that we wrote, and then put into a memory, and now alive, running in the engine. So third, mapping your, and then after that engine, the stock and the memory and the CPU works their way around. Third, mapping your repository to memory based on your file list. Here is exactly where things live during execution. Component, compiled logic, location in OSTEP, code segment, Specific example from your repo, the machine code for rtc-transport.adapter.ts or auth-utils.ts. So this TypeScript code will be compiled to JavaScript engine, whether it's an RTC or LiveKit or authorization utils. Component, local variables, location, the stock, specific example from your repo, the variable token, inside validate-service.ts. So inside of this logic, there's a variable called token. Those are just a stock or the room string in create room. Argument or parameter room. So that room string is just, or room variable is just a stock. LiveKit component, LiveKit state, location, the heap. So a state is a heap because again, it's an object and a data. So specific example from your repo, the actual room object, the local participant, and the media track streams. So the media track streams that contact to LiveKit is also in the heap because it's also a change state. It changed like dynamically. The actual room object, etc. Pointers, component pointers, location, OSTEP, the stock. Specific example from your repo, the reference variable room, so the room, the variable room inside of, for example, validate.service.ts is actually the stock or the pointer to that heap memory, the actual object or the actual room. Component, global state, location, OSTEP, the heap. Specific example from your repo, your Redux or Zastan store, like session-runtime.slice.ts. So those are in the heap because it's a state dynamically changed, lives in the heap, so it persists across different function calls. So since it persists on different function calls, another way of thinking about it is that since it persists, it must be available in different function calls. It must be in the heap because it needs to be large. Fourth, why is this important for your LiveKit app? Because LiveKit deals with real-time streams, understanding the heap is critical. Memory leaks. If you create a room object in the heap but pop the function frame that held the pointer without property disconnecting, that room object stays in the heap forever until the garbage collector finds it. This is why you use effect cleanups in your useVideoCall.es. So we use a use effect cleanup in a useVideoCall service for us to be able to remove the object, the heap object of that video call room. If, for example, the pointer or the variable to that room was popped or were removed without properly disconnecting. The 3 easy pieces connection. OSTEP emphasizes virtual memory. Your LiveKit app thinks it has a clean, continuous stock and heap, but the OS is actually chopping those up into pages and mapping them to physical RAM. When your CPU fetches a LiveKit track, the OS might actually be pulling that page from physical RAM into the CPU cache. So when the CPU fetches like a LiveKit object, the OS might be actually pulling that from a physical RAM into the CPU cache to make it faster. So there's also like concept like that that makes your application fast, because the OS could interfere and add those features, and the Java and the RAM as well, and the database. So to explain this accurately, we have to map your TypeScript code to the V8's engine's memory model, and then map that to the OS 3 easy pieces code theory. In OS step terms, a process has a code segment, a stack, and a heap. Here's how your LibKit app live in those three areas. First, the code segment text. In OS step, this is the read-only part of memory, where the instruction lives. What is there? The V8 engine itself, written in C++, and the compiled machine code of your functions. So this is the bytecode. Now, being passed to a runtime program, which is the V8 engine itself. So this is the read-only part of the memory, because you already compiled it. So from your repo, when you run use video-call.ts or rtc-transport-adapter.ts, V8 compiles this into machine instructions. So if it's currently running, the V8 engine is the one that is converting that or fetching that into an instruction pointer. I guess I forgot the name in the CPU. In the instruction set that is being fetched to a CPU. So the nuance, your actual.ts files aren't in memory. Only the JIT compiled binary instructions for functions like publish struct or handle webhook sit in this executable memory space. So any non-executable like the TS files aren't actually being put by the V8 engine in memory, only the executable in your code, such as the publish struct that signifies a state that eventually become big. Second, the static memory allocation. So this is now so another thing to think about the stock is it's a static, meaning that it doesn't change compared to a dynamic which change. So that's the state, right? The dynamic memory of OSTEP. In OSTEP, the stock is for function frames, local variables, and control flow. It's fast and managed automatically. So VH engine also handles this stock differently from a dynamic object. What is here? Primitive values, local number, boolean, null, and undefined. Pointers, this is the most important part. The stock does not hold your LibKit room object. It holds the address, the pointer, to where the room is in the heap. Execution context. When use auth-session.ts calls validate token, a new frame is pushed onto the stock. When the function returns, the frame is popped or destroyed. So, for example, use auth session.ts. It has like a variable or a pointer to it, like our function or if else that calls the actual object. Then after that, a new frame will be pushed onto that stock when the call is happening. But when the function already returned, it will be removed from that stock in the memory. For others, for other function, variable, or if else flow, to use that stock to then call another function. That's why the frame is popped or destroyed. So from your repo, in summary-logic.ts, a local variable like const count equal to 5 stays on the stock. So if it's a constant variable, it will stays on the stock. The variable const room equals stays on the stock, but it's just a 64-bit number pointing to the heap. So if it's a variable, of course, it is still stay on the stock. So let me reframe. Basically, the value is just being destroyed. What that mean in execution context, that a new frame is pushed onto the stock, and then after it push, of course it will be destroyed, because it's just pointing to that large object because it cannot hold that large object. But for the actual, like for example, const and a variable, it's still in the pointer of the stock that points to a dynamic value in memory. Okay, so third, the heap, dynamic memory allocation. In OSTEP, the heap is for large, long-lived data the developer manages. In C, via malloc. In JS, the garbage collector GC manages this for you. What is here? All objects, every open and close semi-curly bracket, open and close square bracket, which is array. So this open and close semi-curly bracket is an empty object. Map, the new map we described, and a set, which is a nested objects. Closures, this is huge. Another thing is closures. This is huge for your app. If you use transcription.ts as a function, inside the function that remembers a variable, that variable is moved from the stock to the heap, so it doesn't die when the function finish. So basically, the top level variable is just in the stock. But if that variable is actually inside the nested objects, it will not die. It will not push it, or it will not be stored in the stock, but rather it will be stored in the heap, so it doesn't die when the function finishes. Class instances, so your Fiverr's admin instance or LiveKit room instance are also here. Strings in V8, strings are almost always on the heap because they vary in size. So this is an exception for strings. They are mostly, unlike numbers, etc., in the heap because those vary in size. So you usually have like large strings, and they and you usually like not really use this in your app, right? Unless like you want to populate your app with a very large size. So from your repo session dash runtime dash slice.ts Redux states this entire tree lives in the heap. So again, Redux is a tree. RTC dash transport dash adapter.ts, the actual adapter object and its internal buffers live in the heap. So the adapter that we use for LiveKit transport protocol is actually an object which internal buffers lives in the heap. So visualizing your LiveKit app in memory, imagine a specific moment in your app, a doctor in a patient LiveKit room, the TSX, memory area, code segment, real world example from your code, the machine code for handle track, subscribe, logic, stop, the room ID string pointer, currently being processed in a function. So that's when the pop are pushed into the print heap, the Redux store, feature dash flag dash slice.ts, and the LiveKit participant objects. So the machine code for logic, like the handle track subscribe, for example, one of your component has that, it will be put in the code segment, and the room ID that points to the currently being processed function that identifies those function are live in the stock. Where your understanding might be hand wavy, first the string trap. In OSTEP theory, small strings might be considered data. In JSV or V8, strings are objects. If you have a massive transcript in use transcription.ts, that is a massive heap allocation. If you modify that string, V8 creates a new string on the heap immutability. Second, the hidden class, the C++ layer. This is the part OSTEP doesn't cover because it's specific to VM-based languages. V8s create map objects, hidden classes in the heap to describe the shape of your objects. If your participant object has name and role, V8 creates a C++ structure in the heap to remember that name is at offset 0 and role is at offset 8. This is how JS matches the speed of C++. Third, the garbage collection gap. In OSTEP C's example, you free memory in your app if you have a leave a room but use room management.ts still has a reference to it in a global variable. You have a memory leak. The heap space won't be cleared because the root, the global object, still points to it. The profound impediment, closure leaks. Because your app use many hooks, use session chat, use video call, you are creating many closures. The risk, a closure keeps everything in its scope, alive in the heap even if you only need one small variable. If you don't clean up your listeners in UseEffect in patient live kit room.tsx, you keep the entire component scope in the heap forever. So let's just dig deep into the string trap. So if you have a transcript, since a small string are considered data in the OS, but in JavaScript, strings are actually objects. So if you have like a massive transcript, it will live in the heap, and then if you forgot to clean that heap, it will create things like overwhelming memory. So if you modify that string, which is like the data and transcription, the V8 engine will create a new string on the heap because it's immutable. So that's another thing. So data in OS is mutable, in V8 it's immutable. The hidden class, so the C++ layer, this is the part OSTEP doesn't cover because it is specific to VM-based languages. V8 creates map objects like hidden class, like the new map we discussed, in the heap to describe the shape of your objects. So the V8 put that in the heap to describe the shape of the map object. So if your participant object has a name and a role, V8 creates a C++ structure in the heap to remember that name is at offset 0 and role is at offset 8. So this is how JS matches the speed of C++. So if you create basically a participant object, the V8 engine put that into the heap and then remember the name as 0, and then the other or the fields inside that object first is will be defined as an offset 0, kind of like with the C++ offset of setting a variable, and a role is as offset 8 compared to making it a node link memory structure. Third, the garbage collection gap. In OSTEP C examples, you free memory in your app. If you leave a room but use room management, that TS still has a reference to it in a global variable. You have a memory leak. So if you already leave a room and then you still reference that memory in a global variable. So if you use that kind of like a Redux thing, since you are not using a free memory like in C to free that, you don't have that function, that is a memory leak because you already leave it and it's still referencing a global variable that you haven't leave, so the objects are still in the heap. So the heap space won't be cleared because the root, the global object, still points to it. So the profound impediment, closure leaks, because your app uses many hooks, use session chat, use video call, you are creating many closures. So again, like the state management with React, use session chat and use video call are just creating many closure. So it might be good that you have like a hook, but the disadvantage, you are also creating, or you tend to also leak the closure. So the risk, a closure keeps everything in its scope alive in the heap, even if you only need one small variable. So the thing is that if you use that hook, like kind of like a class to manage the state, even if you only need that one variable, those closure will leave, all of those class enclosure will live in the heap. So if you don't clean up your listeners in use effect, so if you don't use the use effect on that hooks to clean up inpatient live kit room, the TSX, you keep the entire component in the heap forever. So even if the variable stops and then you don't have like a use effect to clean it up, therefore it will live there and will cause like a state leaks on your app.